Welcome back to machine learning. This video is going to cover linear classifiers. Before we dive into linear classifiers, we're going to talk about loss. Loss is usually represented by L. L tells us how bad our system's prediction is compared with the truth. Y is the truth, sometimes referred to as the ground truth, but you know it as a label or the class. And Y hat is the prediction. L of y, y hat is a measure of error. Loss is something that you, the programmer, have to decide based on your problem. So it's a hyperparameter. Let's look at some examples. If you're trying to solve a regression problem, where you're trying to predict a real value, like gas prices, then you may want to use a loss like this, the squared loss. The squared loss takes the truth and subtracts the prediction from it, and then squares the result. This looks a lot like the Euclidean distance that we're familiar with, and we've used before for k-nearest neighbors and k-means. That's because it's basically what it is. It's the squared distance between y and y hat. Let's say the truth is y equals 4, and the prediction our model gave was y hat equals 3. Then the loss for that sample would be L of 4, 3, which equals 4 minus 3 squared, which is 1. Similarly, if y hat was 5, you would also get a loss of 1. So the squared loss does not care in what direction you're wrong, just how far away you are from being right. And the further you get from right, the worse it is. A large loss is bad. Let's try it out. If y hat is 10 and the label is 4, the loss is 36. That's not good. Let's try a classification example. If we're trying to predict if the conditions on Tahoe are good for paddleboarding, we might have two classes, good and not good. In this case, we might have a loss that looks like this, the 0, 1 loss, where it's 0 if y is equal to y hat and 1 otherwise. Let's look at an example to see how this works. If we let good equal 1 and not good equal 0, and we have a sample with y equals 1 and a prediction of y hat equals 1, then our loss would be 0. If, however, our y hat was 0, then our loss would be 1. So basically, this loss simply counts up all the samples we get wrong. The losses we have talked about here are just for one sample each, but we want to know how we're doing on the training data as a whole, or the validation data. Error is defined as this equation, 1 over n times the sum from 1 to n of L, yn, y hat n. All of these little n's are the individual samples, and there are capital N number of samples. Since our classifier takes an input sample xn and produces a prediction y hat n, we can think of our classifier/model as a function f of xn equals yn. Then we would have our error defined as this, where the y hat has been replaced by this f of xn. This is just an average loss for the whole set, so we sum up the loss for every sample and divide by the number of samples. What do we want in a good model? We want minimum loss, so we want to minimize our errors. This makes intuitive sense. The 0, 1 loss is very hard to minimize. Let's talk more about that. For instance, if there's a positive training example, y equals 1, and w dot x plus b is negative 0.01, well, then adjusting b upwards by 0.011 would decrease my error by 1. But adjusting it upwards by 0.009 would have no effect. This makes it really difficult to figure out how to adjust the parameters. Let's see this visually. The x-axis is y hat, which is just y times w dot x plus b. So it's just the truth times the prediction. This should look familiar because it's actually the loss that the perceptron algorithm uses. We update if y times a is less than or equal to 0, which means we've made a mistake. Do you remember how we minimize a function? From way back in your academic history, we need to take a derivative. We can find minimums and maximums by finding where the derivative is 0. We can't take the derivative of this function. Why not? It isn't smooth. Okay, so what happens if we smooth it? This is my handiwork. It's a beautiful line. I know you appreciate it. This will work if our only concern is smoothness, but we actually want our loss functions to be convex. Convex functions have a ton of nice properties, but mostly we're interested in being able to find a global minimum. Concave is like a sad face, and convex is like a happy face. What does it mean for a function to be convex? How do we know? Well, there's actually two definitions. The first is that its second derivative is always non-negative. And the second one is that any chord of the function lies above it. So basically, if you draw a point from one side of the function to another, that line lies completely above the function. And you should be able to do that with any 2 points in the function. We love convex functions. They're easy to optimize. We can drop a ball anywhere in a convex function and it will eventually get to the minimum point. We really like the 0, 1 loss because it describes our problem well. There should be penalties when we get the wrong classification and no penalty when we get the right one. But because it's difficult to optimize, we have to come up with some different options called surrogate loss functions to approximate the 0, 1 loss. These surrogate loss functions are convex, and so they have all the nice properties we want in a loss function, while still capturing the idea of a 0, 1 loss. These are our surrogate loss functions. There are many, but these are some of the most common ones. We're going to go through each of them in turn. Here they are plotted. What are the big differences between these loss functions? The first is how upset they are by erroneous predictions. And the second is how they deal with very confident correct predictions. Let's go through each. The 0, 1 loss treats all errors the same, and they're given a loss of 1. And when it makes a correct prediction, they're all treated equally, and it's given a loss of 0. The hinge loss, so named because it looks like a hinge. It's the green dashed line. Errors are linearly increasing as the error gets worse, with a minimum loss of 1. Correct predictions are linearly decreasing from 0 to 1, and after that, all predictions are treated the same. When y times y hat equals 1, that means they are exactly the same, both 1, and they're treated as a correct prediction. The logistic loss, errors increase logistically from 1. The farther the prediction from the truth, the larger the loss. Correct predictions decrease logarithmically from 1, 0 on the x-axis. The more confident the prediction, the lower the loss. Think about this. If we have y equals 1 and y hat equals 1, this should be perfect and give a loss of 0. But it doesn't. A prediction of y hat equals 2 is better than y hat equals 1. Exponential loss. Errors increase exponentially from 1. This is much worse to make a mistake in this case than any of the other loss functions we've seen. Correct predictions decrease exponentially from 1, so the loss decreases much quicker than the log loss on the correct side, but similarly, the loss never actually reaches 0. The squared loss, which is sometimes referred to as the least square. Errors increase exponentially from 0, when y equals y hat is the only time the loss is 0. Correct predictions increase exponentially from 0. Overly correct predictions are treated just like incorrect predictions. This loss function is interested in exact prediction. More often, this is used for regression problems than classification problems. Now that we have covered loss, and you know some common loss functions, let's look at linear classifiers. So far, we've learned about the perceptron as an example of a linear classifier, but most of the time our data is not linearly separable, and we would like to use a linear classifier anyway. The perceptron algorithm will not converge if the data isn't linearly separable, so we have to find some other way to train our linear classifier. We want to find the separating hyperplane that makes the fewest errors. We can write this down as a formal optimization problem, like this. Let's unpack this. We're minimizing over two variables, w and b, so we want to minimize this function and return the w and b that gave us that minimum. The objective function is the thing we're trying to optimize. In this case, we're just minimizing. That's the optimization that we're going for. The objective function in this case is just the error rate. It's the 0, 1 loss of the linear classifier parameterized by w and b. This 1 with brackets is called the indicator function. It's 1 when the stuff inside the brackets is true and 0 otherwise. The optimization problem is very hard to solve efficiently, given not linearly separable data. So what do? We want the problem to be easier, and we also want the model to generalize well to unseen data. So we add a regularizer. This is our regularized objective. We've added this lambda r of WB. Now we're trying to optimize a trade-off between a solution that gives a low training error, which is this portion of the equation, and a solution that is simple, which is this second term. Lambda is now a hyperparameter. What do we want from R? R should be convex, so it's easy to minimize. And the common desire is to have small weights. But why? Let's say we have a sample x with label 1. We would assume that a point nearby, x prime, would also have a label of 1. What if we take x prime to be x, but with x1 changed by a small amount, e? The difference between y hat and y hat prime would be EW1. If W1 is small, the difference is small. But if W1 is large, then the difference can be very large. And we don't want it to be. So small weights make it such that samples that are nearby each other have similar predictions. What could R be? There's many different options. Here are some common ones. This is the norm R, which is just the L2 norm of W. You'll notice that B isn't included here. This is typically because we actually make W one dimension longer and we include B at the end. This is convex and smooth, right? That's important. Another option for R is the squared option. So this is exactly the same as the norm, but we just square it. That gives us nice properties. We'll see that later. Another option is the absolute. What about zero weights? What if we want to learn that some features are irrelevant? This is very useful. We can do this by deciding that R should be a counter. So it counts up the number of weights that are 0. All right. Now we have a big, ridiculous equation that we're trying to optimize. How do we actually do it? With a technique called gradient descent. If I'm blindfolded and standing at the edge of a valley and my goal is to reach the bottom, how might I go about doing that? If you take small steps in each direction, you can identify the steepest direction and step that way. You can repeat this process until you are at the bottom of the valley. This is called gradient descent. We find the gradient of the valley, which is going to be our function, at each step, and we take a step in the opposite direction of the gradient. The gradient of a function is the direction of greatest increase, so we step in the opposite of that direction. Now, we are at a new location and we do it all over again. Gradient descent is very simple. If we're at a location x and we want to move, we subtract some eta times the derivative of the function, or the gradient, which I've denoted here as g. G of x is the gradient of f. Remember that the gradient is denoted like this. So we can rewrite the equation and it looks like this. Now that we know that we need to do gradient descent to find the minimum of a function, we know that we need to use gradient descent to optimize our loss functions. Let's look at an example with an exponential loss and a norm regularizer. Here we have an exponential loss, this one right here, and a norm regularizer, a squared norm regularizer. Where did this 1/2 come from? It's a choice that we make to make the gradients cleaner. You'll see in just a second. But generally speaking, a constant added to a loss function isn't really going to change its behavior. Why is this now L of w comma b and not L of y hat? Y hat is defined entirely by the sample xn and the model parameters w and b. So since we're not calculating the loss with respect to one sample, but rather the loss over the entire training set, we really only need to know what w and b are to calculate that. And then we just iterate through all the samples xn with labels yn. Let's take the gradient with respect to b first. Remember that taking the gradient, we can bring it into the equation and separate it out into its parts. There's no b in the regularization term, so this becomes simply this. The derivative of the sum is the sum of derivatives, so we can pull the derivative inside the summation. Remember that the derivative of e of f of x is f prime of x e to the f of x. So we get that the gradient of L with respect to b is this. Why? Because the derivative of negative yn w dot xn plus b with respect to b is just negative yn. So in the end, we have this. We take this equation and we use it to update b. So we take b equals b minus eta times dl db. Okay, but what the heck is actually happening here? Consider a sample with yn equals 1, so we have a positive sample. As wx plus b approaches infinity, this term approaches 0. This means that the entire expression approaches b equals b as the prediction is correct. As wx plus b approaches negative values, this term is positive and increasing, so b will increase. This is exactly what we want. Remember the perceptron update rules? B equals b plus y. We add 1 to b if the prediction for a positively labeled sample is incorrect. Now that we have updated b, let's work on updating w. The gradient of L with respect to w is this. Let's start with the second term. What is the norm of w squared? Let's expand it so we can better understand how to take its gradient. Here it is, expanded. Remember, the gradient is just each of the partial derivatives in a vector together. Let's do that. Here we have the partial derivative with respect to w1, with respect to w2, and with respect to wd. Okay, we can combine all of these into a vector and we get this. 2w1, 2w2, all the way to 2wd, which is the same as 2 times the vector w. Don't forget we have that lambda over 2 in front, so the second term becomes just simply lambda w. Nice and simple. Now let's do the first term. We can bring the gradient inside the sum. And we get this as our final expression. Combining the terms, we finally have that the gradient of L with respect to w is this. We can then update w as follows. For correctly classified points, this term heads towards 0, and w is simply updated using the regularization term to make w small. For incorrectly classified points, the update ends up being w equals w plus cyx minus eta lambda w, which without the regularization term looks like the perceptron update. What is c? It's small if the points are close to being correct, and large if the points are far away from being correct. The lambda w portion of the update simply shrinks the weights towards 0, which is exactly what we want. W equals w minus lambda w, which equals 1 minus lambda times w. And with lambda greater than 0, we know that this operation is just shrinking w, as it should. Success of gradient descent depends on the choice of the step size, eta. When do we stop? This convergence result suggests a simple approach to deciding when to stop optimizing. Wait until the objective function stops changing by much. An alternative is to wait until the parameters stop changing by much. A final example is to do what you did for perceptron, early stopping. Every iteration, you can check the performance of the current model on some held out data and stop optimizing when performance plateaus. Why are we doing all of this? Where did all this math come from? Why are we doing this? Remember, we want a linear classifier for data that isn't linearly separable. What we could do is we could just run the perceptron algorithm and stop it early because we don't know if the data is linearly separable or not. Or we could choose a loss function that's appropriate for the problem we're trying to solve and use gradient descent, and that will give us a W and B that describe a linear classifier but doesn't completely separate the data. So we want a linear classifier because they're simple and they're easy to understand and they generally work really well, but we are dealing with data that can't be linearly separated. So we're using an optimization approach to find our W and B. That's it for linear classifiers. The next topic is practicalities of machine learning. This will be covered after the first midterm.